What's up, friends? Welcome back to Neil's Not So Boring World of Chemistry, where today we're going to teach you how to go from interesting chemical reactions like this to fully balanced chemical equations like this in just a few easy steps. Hit the like button, subscribe to the channel, and get ready to learn. What's up, everybody? Welcome to Neil's Not So Boring World of Chemistry. Let's go into the lab and take a deeper look. Okay, everyone, so as promised in this video, we're going to go from a chemical reaction that we've witnessed to a chemical equation, which is a series of symbols that tells the story of what happened. Before we do that, we should always ask a question. Do we have a chemical change? In order to be clear about whether or not it's chemical or physical, I like to go over the signs of typical chemical reactions. Now, let's start with visual. When we watch the video of the steel wool ignited, what do we see? Well, first and foremost, we're mesmerized by the heat and light that's given off. Energy changes are telltale signs of chemical reactions. You should be warned, though, sometimes it's not in the form of heat being released, but energy being absorbed by the chemical system. And this would result in things feeling really, really cold. Now, if we look at an image of the steel wool before and after, you should notice a color change. And color changes are very, very common when dealing with chemical changes. Now, one thing I can't translate to you in this video was the production of an interesting odor. Odor changes are also really strong signs that you're dealing with a chemical reaction. Let's take a look at what happens when we actually track the mass of this steel wool as it's going through this interesting process. Now that result is very unexpected. We're used to seeing things burn and in the process lose some of their mass. But in the case of the steel wool, we actually saw the mass increase. Now, whether it's a decrease or increase in mass, remember, mass is keeping track of atoms. And this tells me that there were probably some atoms added to the steel wool, and that would constitute a chemical change as well. Now, to be clear, the color change, the mass change, the change in energy, and the odor production that we saw in this particular instance doesn't have to happen in every chemical change out there. But these are just some very typical common signs to look for. You want to contrast that with things like state of matter changes. So for example, when ice melts or rubbing alcohol freezes, these are not chemical reactions. They don't feature any of the signs that I just explained to you, and therefore we wouldn't be expected to write a balanced chemical equation for those processes. Now let's dive deeper into the reaction itself and start to come up with some of those symbols that we're going to need to make this equation complete.
Okay, so now that we've established that we do have a chemical reaction, it's time to look at some steps that are going to help us change that reaction into a series of symbols known as a chemical equation. In step 1, we need to identify reactants and products. What are we using in our reaction and what was made? Now, of course, the most obvious reaction is this steel wool. And what many of you may not know is that steel wool is principally composed of the element iron. So we know we're going to have iron on the left side of our arrow. Was there any other reactants? Next, we know that there's a product. Our iron changed. In this before and after photo, you can see it looks significantly different. So on the right side of the arrow, I need to somehow represent this iron, which seems to be in a new form. We'll figure out how to do that later. Here's a quick tip. Sometimes students think that because this reaction happened with a battery, that somehow the battery needs to be included in the equation. Sources of energy such as batteries or fire need not be written in chemical equations, even though they're very important participants in the process. Okay, so are we really just going to have one reactant and one product in this equation? I don't think so. Please remember that we saw an increase in mass when we watched the video of this reaction on the scale. Ask yourself a question. where could that extra mass have come from? It's important to remember that more mass means more atoms. And there's really only one place where those extra atoms could have come from, because I certainly didn't add them to the beaker, and that would be the air. Anytime we carry out a reaction in an open container like a beaker or a test tube, air is in the mix. And it's so easy to forget or overlook because our eyes can't see those molecules. Now, you may know that air is principally made of two gases, nitrogen and oxygen. Now, because nitrogen tends to make up the majority of air, sometimes people think that's the most likely reactant. But actually, oxygen tends to be much more reactive. Now, if you're wondering if I'm going to explain why oxygen is more reactive, I'm not. I can't get into that in this video, but here's some clues for the curious folks out there. Compare the Lewis structures of N2 and O2, and also think about electronegativity. But back to oxygen for a second. It's really important to remember that oxygen, although it can't be seen, is always around. Anytime there's a reaction that involves explosions, fire, or burning, I would consider oxygen as a potential player. Okay, so now we have a better sense of what happened. We had some iron, it reacted with some oxygen in the air, and we made some kind of new iron compound that is made of iron and oxygen atoms, because remember, the mass went up. But how are we going to change these words into symbols? This is probably the most important part of the process of writing a chemical equation. Dare I say also, it is the most challenging. Step 2 is representing reactants and products with correct formulas. Now, in most chemical equations, your reactants and products will fit into one of these 5 categories. And I did say most, not all. We've got metals, we've got diatomic gases, we've got ionic compounds, we've got covalent molecules, and we have strong acids. So our metals are just singular metallic elements, like iron, copper, gold, and you're just going to write them as a single atom. The diatomic gases need to be memorized. They are fluorine, nitrogen, oxygen, bromine, iodine, hydrogen, and chlorine. There's many different ways to do this. Hybron Cliff, have no fear of ice cold beer, and my favorite, F no bro, I hate class. Now, the ionic compounds and covalent molecules are going to make up the majority of your reactants and products. If you need guidance on how to pick whether something is ionic or covalent, please pause the video and read over these directions. Lastly, we have our strong acids, and again, these need to be memorized. They are Hibber-Hickel, HNO3, HCl4, H2SO4. Now, it's important to know their actual names as well as their chemical symbols. But again, most of the time, these are the 5 types of things you're going to see in common chemical reactions. Now, of course, there are other types of compounds out there, but this is what you should focus on as a beginner. So, what did we have in our reaction? Well, we said we had iron. Now, since iron is a metal, I'm going to represent that as just a single Fe atom. We also said we had oxygen, and oxygen is one of the diatomic gases, so it needs to be written as O2. Lastly, we have iron and oxygen combining. That's an ionic compound because it's a metal and a nonmetal. And remember, we make those formulas by thinking about the charges of the ions. Now, we're not even close to being finished yet, because one thing that's lacking from our chemical equation at this point are states of matter. In step 3, we have to decide whether the reactants and products were solids, liquids, gases, or aqueous. Here's some rules to follow. Metals are going to be solids, and solids are represented by a lowercase s. Diatomic gases are, well, gases, so they're represented with a lowercase g. Acids and some ionic compounds can be aqueous, which is represented with an AQ, and our covalent molecules can really be anywhere over the spectrum. Solids, liquids, which is a lowercase l, or gases. But back to that aqueous thing. You may not be so sure of what that means. Aqueous, which is represented by the symbol AQ, tells us that the substance has been dissolved in water. Anything that's described as a solution is aqueous. Acids are also always going to be aqueous. And if a question says something was dissolved in water or mixed with water, that doesn't mean you need to add H2O to the equation. Just put the symbol AQ next to it and you're done. Okay, so what were the states of matter in our chemical equation? Well, iron was a solid, oxygen was a gas, And this ionic compound, iron oxide, is also going to be a solid because, of course, we didn't dissolve it in water or anything like that. Now, I want you to take a really close, critical look at the equation we've written. Does it seem complete to you? Does this make sense? Pay attention to the numbers. I think there's a problem with this, and that is that on one side of the equation, we have more iron atoms and oxygen atoms than on the other side. This means we violated the law of conservation of mass, and now we need to balance the equation. Let's go back into the classroom to learn how to do just that.
Okay, everyone, now we're ready to balance this equation. This is an integral step where we make sure that the law of conservation of matter is being observed. Simply put, do we have the same number of each type of atom on the left and right side of the arrow? Now you can look at my model and my t-chart and see that we have some problems. There's more iron and oxygen on the product side than the reactant side, and this is never okay. How can we fix this? We're allowed to put coefficients, which is to say whole numbers, wherever you see a purple line. Now we don't have to put one everywhere, only where needed. We're never allowed to change the subscripts or the small numbers because we need to maintain the integrity of the chemical formulas. So the easiest thing to fix initially would be to increase the number of iron to 2 on the reactant side. So I can put a 2 here and then update my t-chart to represent that. I'm also going to add a second iron atom to my model. Next, I'm going to try to fix the oxygen issue. Now this is a little more complicated because the oxygen is 2 and 3, and I have to find a number that they can both become through multiplication. In other words, the lowest common multiple. I think you would agree that 2 and 3 can both be multiplied to equal 6, so let's do it. Over here, if I put a 3 times 2 gives me 6 oxygen atoms. I can then add more oxygens to my model to represent that change. So there we have 4, and now we have a total of 6. But how can we get 6 on the product side? Well, multiplying 3 by 2 will give you 6, so let's do that. Now, while I was just trying to fix the oxygen issue, which I did, you'll notice I've also impacted the iron. When you put a coefficient in front of a chemical formula, it gets distributed to everything in that formula. So now I have more iron than I had bargained for. I have 4 versus 2. Am I able to fix that? Sure. Before I do that, let's update the model. So I'm going to grab a few more irons and a few more oxygens to represent this change. 4 irons, 6 oxygens. How can we get 4 on this side? You guessed it. We're allowed to change this coefficient from a 2 to a 4. Now that means I can update my table. And this is exactly what we want to see. The same number on either side of the line for a particular element. Can add a couple more irons in here. And now you can see we have a balanced chemical equation that's reflected in both the model and the t-chart.
Okay, so there's only one way to know whether or not we've learned from this video, right? We have to try a practice problem. In this question, you're asked to write a balanced chemical equation for the following process. Sulfuric acid reacts with calcium hydroxide solution. After mixing, water and calcium sulfate are formed. Now we're going to do this in 4 easy steps. So after I read the directions for each step, pause the video, think about your answer, and then check your work. In step 1, you need to identify reactants and products. Read the sentences and use context clues to decide what should go on the left side of the arrow versus the right side of the arrow. Okay, so our reactants are sulfuric acid and calcium hydroxide. It says in the first sentence that these two substances react. Our products are water and calcium sulfate. I know this because of the word formed. Step 2. Now we have to write chemical formulas. This is where you consider whether each substance is a metal, a diatomic gas, an ionic compound, a covalent molecule, or a strong acid. Feel free to go back into the video if you don't remember how to do this. Okay, so sulfuric acid is a strong acid, which we've memorized. It's H2SO4. Calcium hydroxide is an ionic compound made up of the metal calcium and the polyatomic ion hydroxide. Water is a common molecule, and calcium sulfate is another ionic compound made up of the metal calcium and the polyatomic ion sulfate. Step 3. Now we have to decide on our states of matter. read through the sentences and look for context clues as to whether these things are solids, liquids, gases, or aqueous. Okay, so first of all, sulfuric acid is going to be aqueous because of the fact that it's an acid. They always are. Calcium hydroxide is an ionic compound, and in this case it's described as a solution, which means it's aqueous as well. Now, water is almost always a liquid, unless of course you've been told that the water is evaporated or is a gas. Finally, this calcium sulfate is also going to be aqueous because of the fact that it's mixed with water. Now it's time to balance the equation. In this step, we ensure that there are the same number of atoms of each type of element on either side of the arrow. Okay, and in order to make sure this is balanced, all I had to do was add a coefficient of 2 in front of the water molecule. So that's going to wrap up this video. I want to thank you all for watching and supporting the channel, and I'll see you in the next one.